In topic 4, we're going to be looking at functions defined as quotients of polynomials. That means we'll have two polynomials dividing with each other, and we're going to really look at their graphs and what key features they have, and also where certain behaviors happen. We want to start by talking about the area of a rectangle. Most of us know the formula, which is length times width. So if you look at the picture here, they give us a long example of a rectangle where we have 72 times 2. Well, that'd be an area of 144 square units. Same thing here, 24 times 6 is also 144 square units. You could make a table of various lengths and widths that could be had to make an area of 144. And the one thing that's constant is that the area is always the same. So we also could rearrange this equation with length times width equals A to be, hey, if we divide by L on both sides, we get this one. Or say we divided by W on both sides, we would get this bottom one. So if we divide by W here, we would get this bottom one. Note that all three of these equations are the same thing, just rewritten a little bit differently, solving for a different variable. We would like to say that L varies inversely with W, especially when it relates to this equation right here. One might say in this top equation that W varies inversely with L. Inversely is going to be one of our key words in this first section as we begin to look at inverse functions. In 4.1, we're going to talk about how inverse variations or relations are related to their reciprocal functions. So kind of big words here, but let's just look at this example 1. For inverse variation, we're talking about a relation between two variables, such as where one variable increases, the other one decreases, and they need to decrease proportionally. Let's go back to this table. You can see that as our length is going up, as we're getting longer and longer lengths, our width is going down. We're losing the W value, which makes sense because in order to keep the area constant, when one value goes up, the other one must go down and compensate for it. But it can't just jump down by, say this can't just go down to 140. It needs to go down proportionally. That means if you check and multiply, they'll come out to the same area. So to determine if a set of values, an XY table, is actually an inverse relationship, think back to that area model. Anytime you had length times width, it had to be the same area. That's because your area was constant, and as the length went down, the width would have to go up, or vice versa. So let's check. If you had a table with length 1 and width 12, the area would be 12. Now if your length went up to 2 and the width went to 6, your area is still 12. I'm going to try all of these combos in the table, multiplying x times y essentially. So I'm basically taking x times y to give me this total value at the bottom. It's important that you check all of them, but it does happen to be that all of those products are 12. Therefore, we would say, yes, this is an inverse variation. In your packet, the study tip really is just to be sure that you check every pair of XY combinations to make sure that the relationship is inverse. You could try this part B on example 1 and check if your answers are correct. Same thing here for the try it. You would take your x, pretend this is your length, and this is your width y, and check if each of those combos actually multiplies to the same value. Looking at part B, I went ahead and tried the x times the y and got 19.8, and when I checked the second pair of numbers, multiplied to 27.5. So we would say, no, this is not a representation of an inverse variation. If you find one that fails, show's over. So some formulas or a concept to remember here. We checked the x times y variables, and we mentioned how you can rearrange these, but not every set of values is representing length times width. And in our first case, area was always constant. We refer to that constant as a k. So you could think of this as A equals L times W. There'll be other things in the real world that represent inverse variation, but for now, just remember that K is what we call our constant of variation, fancy word for the constant that each set of inverse variables should multiply to. And again, these are the same formulas, just solved for various variables. Now looking at example 2, they say if x is 10 when y is 3, write an equation to represent the inverse variation. So I'm going to use this idea. I know the x and the y, so I would say, hey, 10 is x times 3 is y. That means my k value is going to be 30. That means that is the constant we always need to reach. So now they ask, find the value of y when x is -6. We can now say that we want to find the y value, but we know the k is 30, and we got that from here by using our first combo of values. They told us it is an inverse variation, so we can know that when you multiply the xy, you want to get a same constant. So if k is 30, we want to find the y. They tell us the x is -6, and so I'll put -6 in here. Turns out that 30 divided by -6 is a -5. You can try these triads in that same way. Don't let the fraction make you worried. If you had your 6 for your x times your y of 1/2, it's just going to give you 3. That's your constant. So now that you know your constant, you can solve this problem below. For example 3, they just bring in another real-world application. String length s varies inversely with frequency f. So since they vary inversely, just like the area length and width did, I write them in the same formula. Now they tell us a 26-inch string length and a frequency that it has is 329.63. We can find our constant. You would just multiply those two. Once you found your constant, you're going to be able to use that same formula. They say, what is the frequency? You'd have your f, plug in your constant, and divide by the length of the string. So this constant, remember, you would get that answer, plug it in over here, and you'd have your frequency. You can check your packet for the answer on that one, and you could also give the triad a try. So your final idea here is we've been dealing with that constant. Now, most equations in math say y equals some sort of equation. That's why this is one of the most commonly used forms of that inverse variation, because it has y equals. This is actually called an inverse function. That's because as x goes one way, the y goes the opposite way. They're kind of like opposite. Our parent inverse function is 1 over x, and we're going to be dealing with that quite a bit here for the rest of the topic 4. On example 4, they actually want you to graph this inverse function 1 over x. Now I've done that here, and I just used this tables of values. You might say, how did you get these numbers? Well, try taking in x is 0 and divide by it. So 1 divided by 0. I took this x value and plugged it into the equation. It's simply plotting values. You could definitely use Desmos or a graphing calculator. When I did that, you'll notice that this graph has these little purple dots, and it kind of rides out through here, and then also right down here. You'll notice this weird behaving thing at the line at x equals 0. It's what we call an asymptote. It's a value that makes a function undefined. Look at 0. When you put 0 in for x, you can't divide by 0. 1 divided by 0 is an undefined value. So it makes the function undefined, and therefore it's an x value that the graph does not cross. When you look at that, you can just see this general shape. This is the basic shape of inverse functions. And now we're going to remember transformations from topic 1 and apply those to these types of graphs as well. Quickly on the try it for number 4 here, they said graph 10 over x. So it's not the parent function anymore with a 1 up top. It's got the 10, and see what happens. Notice that the 1 over x is the red graph. That's the parent graph. And the 10 over x, it just kind of pushes out from the origin, if you will. It's got that same look, and it definitely has that asymptote there at x equals 0. They'll ask you things about the domain and the range and the asymptotes. We'd say the vertical asymptote here is at x equals 0, because it can't touch there. There's also going to be a horizontal asymptote here at y equals 0. You can kind of see how it's riding up along there and not touching it. More on that later. The domain is all numbers except 0. So all except x equals 0. And that's because right here, when you put 0 in the denominator, it's undefined. Your range, notice how it goes up forever right there and down forever right there. Positive infinity to negative infinity. Except for it also doesn't hit 0. You can see how this rides that line and it's never going to hit 0. Finally, for example 5, they bring in some of the transformations that we previously discussed in topic 1. Remember that a number next to the x always translates left or right from the parent function. So if it said minus 3 like it does here, that's going to move it to the right 3. And if it's outside here, that plus k value translates it up and down. So here is our parent function, 1 over x. Each of these points, for example here, I know 1, 1 is hit. That's going to move right 3 and up 2. Same thing here. This point right here is going to move right 3 and up 2. These will kind of be where your new curves are, but what's also interesting is remember how the asymptote used to be at 0? Now it's actually at 3. That's your vertical asymptote. And what that means is this graph's going to kind of go, and also we could say that when it used to not hit the x-axis, that's going to move up 2. So here would be your other horizontal asymptote at y equals 2. This is at x equals 3. It moves your asymptotes as well. So our new graph is something like this. It just takes the entire picture, not only the dots of the graph, but the asymptotes of the graphs, and moves it as well. Notice your domain and range. They're still all real numbers, except for x cannot be 3, because when you put a 3 in there, it will make the denominator undefined. And because y used to not be 0, now y cannot be 2. So this is your domain, and your range is all except y cannot be 2, because we see how it doesn't hit that 2 now, just like it didn't used to hit that 0. A lot of times these graphs you can get by just plugging in x, y values, and sometimes we'll just check with Desmos. But if you had asymptotes on the original 1 over x parent function, they're going to translate just like the points would.